Ever wondered how your favorite social media filters fit so perfectly on your face? That's facial landmark detection technology at work. It's a fascinating blend of computer vision and artificial intelligence that enables machines to identify key points on a human face. These points, or landmarks, map out the essential features such as eyes, nose, mouth, and the jawline. In total, there are 68 landmarks that a machine can detect, allowing for a detailed understanding of facial structure. This technology is not just for fun filters on social media. It has serious applications in fields ranging from biometric security to emotion recognition and even medical diagnostics. However, today we're going to focus on the fun side and help you unlock the secrets of this fascinating tech. We are going to show you how to create this magic yourself using Python and DLIB. Are you ready to dive into the world of facial landmark detection? See, to kick things off, we need to import CV2 and DLIB, our main tools for this project. CV2, or OpenCV, is a powerful library used for image processing. It helps us load, manipulate, and visualize images. On the other hand, DLIB is our go-to for facial recognition. It's equipped with pre-trained models that can detect faces and predict facial landmarks with ease. With these libraries, we're ready to dive into the world of facial recognition. Next up, we initialize DLIB's face detector and load the landmark prediction model. These two components are essential for our facial landmark detection. The face detector does exactly what it sounds like. It detects faces in our image. It's like a scout, scanning the terrain and marking where each face is. The predictor, on the other hand, is a bit more of an artist. It takes the faces that our detector has found and maps out the facial landmarks on each one. Think of it this way. Our detector is the one who finds the canvas, and our predictor is the one who paints the picture. Both are necessary to create a complete piece of art. By initializing our detector and loading our model, we're essentially preparing our tools. We're getting everything ready to create that perfect sketch of facial landmarks. After initializing our detector and loading our model, we're ready to process our image. Now it's time to load our image and convert it to grayscale. The first line of code you see will be used to load the image. This can be any image you want to use for facial landmark detection. Make sure the path to the image file is correct and you're good to go. The image is loaded as a colored image by default, but why do we convert it to grayscale? Well, converting an image to grayscale simplifies the image processing. The grayscale image has only one channel compared to the 3 channels of a colored image, red, green, and blue. This reduces the amount of data to be processed, making the detection faster. And don't worry, it doesn't affect the accuracy of our facial landmark detection. With our image loaded and processed, we can now detect faces. Stay tuned to see how we find faces in our image and how we draw the facial landmarks on them. Let's get to the exciting part, detecting faces in our image. We're going to use DLIB's face detector, which we've initialized earlier. This function takes our grayscale image and scours it for faces. It's like a digital detective searching for the telltale signs of a face in the image. But how does it know what a face looks like? Well, the detector has been trained on thousands of images, learning to recognize the patterns and shapes that make up a face. It looks for areas of the image that match these patterns, and when it finds a match, it marks that area with a rectangle. This rectangle is our detected face. And there we have it. We've scanned our image and found the faces hidden within. Now that we've detected faces, we can predict their facial landmarks. But we'll get to that in the next scene. Stay tuned. For every face we've detected, we can now predict facial landmarks. You might be wondering what these facial landmarks are. Well, they are a set of 68 specific points on a face that map out key features like the eyes, eyebrows, nose, mouth, and jawline. They are crucial for various applications, including face recognition, emotion detection, and even those entertaining filters you see on social media. To predict these landmarks, we use a function from the DLIB library. This function takes the grayscale image and detected face as inputs and returns a list of 68 coordinates, each corresponding to a facial landmark. Our code will look something like this for face and faces. In this snippet, face is a rectangle object that contains the coordinates of the face detected in our image. We pass face in our grayscale image, gray, to the predictor function. This function then uses the landmark prediction model we loaded earlier to find the 68 facial landmarks. Once the function finishes its job, we have a set of landmarks for each face in the image. Each landmark is a point object with its own x and y coordinates. We can access these coordinates using the part method, like x equals sign landmarks, part n. In this line of code, n is the index of the landmark. We can loop over all the landmarks from 0 to 67 to get each one's coordinates. After predicting our landmarks, it's time to visualize them on our image. The next step is to draw these landmarks on our image, which we'll cover in the next scene. But before we move on, take a moment to appreciate how remarkable this technology is. With a few lines of code, we're able to map out the intricate details of a face in an image. The possibilities are endless, and I can't wait to see where this technology takes us in the future. Let's bring our landmarks to life by drawing them on our image. Now, this is where we really start to visualize the facial landmarks. We've detected the faces, we've predicted the landmarks, and now it's time to make them visible. So, how do we do that? By plotting each landmark as a point on our image. We're going to use a simple loop to go through all 68 landmarks for each face we've detected. We'll grab the x and y coordinates of each landmark and draw a small circle at that location. Here's what the code looks like. We set up a loop to iterate through the range from 0 to 68, representing each of our landmarks. For each iteration, we extract the x and y coordinates of the landmark. These coordinates are then used to draw a circle on our image. The 2 in the CV2. Circle function is the radius of the circle, and the 25500 is the color of the circle in RGB format. In this case, it's red. The +1 at the end is to fill in the circle. Python copy code for n in range 068. With this code, we're essentially sketching the landmarks onto our image. Each landmark becomes a red dot, and together they create a map of the face's features: eyes, nose, mouth, and even the jawline, all marked out for us to see. So after running this code, what do we get? An image with all our facial landmarks clearly marked. It's a striking visualization, isn't it? You can clearly see the detailed structure of the face, picked out in red dots. It's a powerful way to understand how facial recognition technology identifies and interprets facial features. With our landmarks drawn, let's take a look at the final result. It's more than just an image. It's a testament to the power of technology to understand and interpret the world around us. And there you have it. An image with facial landmarks clearly marked. We've journeyed through the process of facial landmark detection using Python and DLIB. This fascinating tech, which is the backbone of those fun social media filters, has been demystified. We began by importing our essential libraries, CV2 and DLIB, the gateways to our image processing and facial recognition magic. We then initialized DLIB's face detector and loaded the landmark prediction model, our digital artist that sketches out facial points. Next, we loaded and processed our image, converting it to grayscale to make detection faster and efficient. This led us to the exciting part: detecting faces in our image. Every detected face was marked with a rectangle ready for the next step. We then predicted facial landmarks for each face detected. Remember, there are 68 of these landmarks, each mapping out key features like the eyes, nose, and mouth. Finally, we drew these landmarks on our image. Each point was visualized as a small circle, clearly marking our 68 points and bringing the magic of facial landmark detection to life. This journey has shown us the intricate steps that go into creating the magic we often take for granted. Whether you're creating fun filters or conducting serious research, the possibilities of facial landmark detection are endless. Share your ideas in the comments and keep exploring the world of tech.